Hello everyone, this chapter I'll talk about technical principles of HBase. After this course, we'll be able to know system architecture, key features, basic functions, and some enhanced features of HBase. First, let's take a look at the introduction to HBase. HBase is a column-based distributed database built on top of the HDFS, which means that HBase uses HDFS as its file storage system with high reliability, performance, and scalability. I'll explain column-based later. HBase is actually similar to Google's Big Table, designed to provide quick random access to huge amounts of structured data. So in the same way, we can use HBase to store and process big table data, which has billions of rows and millions of columns. And it also provides real-time read or write access to data in HDFS. Also, HBase uses Zookeeper as the collaboration service. So in short, HBase is the Hadoop database, a distributed, scalable big data store. We know that Oracle, MySQL, and many common databases are actually relational database, RDB for short. But HBase is NoSQL, not only SQL, which usually refers to non-relational databases. Most common ones are MongoDB, Redis. So let's take a look at the difference between them. HBase is distributed, which is easy to understand because it's built on top of HDFS, and it's column-oriented. What is column-oriented? Normally, in a table, in Oracle or MySQL, data is stored by rows. Data can be added, modified, or read by row. But when we need all data in the name column, we may need to read the entire row to get the data. So in this case, we may read some unnecessary data. That's why we find another way to store data, which is by column. Data can be read or calculated by column, but when a row is read, we need multiple I/O operations. So in HBase, data is stored by column. This is what we call column-based. It's different from relational databases. Let's go back to see other differences. Here, relational database has fixed data structure. What does it mean? For example, we have a table with employee data. The columns include ID, name, phone, and address, and the attributes of each column are all fixed. So we need to predefine the data structure before we put actual values into the table. However, HBase doesn't need to. We can make dynamic extension of columns. For example, an employee table in HBase. For first record, we have ID and name. For second record, we have ID, name, and phone. For third record, we have ID, name, and address. Each record could have different columns. Columns can be dynamically extended. Also, HBase supports common commercial hardware, which costs less when making expansion, while the expansion of RDB costs much more. And the relational databases are I/O intensive. So these are the differences between them. As for the application scenarios of HBase, it can be used whenever we need to provide fast random access to massive data, or we need high throughput, or we need to process structured and unstructured data, like text files, images, videos, web pages at the same time. Or we do not require the ACID features of traditional relational database, which are atomicity, consistency, isolation, and durability. They are a set of properties that ensure normal database transactions. Atomicity requires that each transaction be all or nothing. If one part of the transaction fails, then the entire transaction fails. Consistency means that, for example, consistency determines that A plus B equals 10. If a transaction changed the value of A, B must also be changed. Isolation ensures that two or more transactions will not be executed in an interleaved manner because this may cause data inconsistency. Durability means that after a transaction is executed successfully, modifications made on the database are retained permanently. No rollback is performed unless necessary. When we don't require any of these four features, we can use HBase. Infusion inside Hadoop, HBase is a basic component for storing massive data. It's a column-based distributed storage system built on top of HDFS. And there are cases that Hive and Spark depend on HBase for upper layer analysis. Take a look at the storage mechanism. How data is actually stored in HBase. While data model in HBase is key value, which means data is stored in the form of key value pairs. Key is used to quickly query a data record, and value is used to store user data. But each key corresponds to many values. Like in Huawei, everyone has an ID number. We can take this as a key, which can correspond to name, age, phone, address, and many other information. But when we use the ID number to quickly query how to make sure we get the name value, not the age. That's why key value must store some description of itself, such as timestamp and type information. This requires some structure space. RDBs predefine the data structure in the database as a series of tables containing fields with well-defined data types. In contrast, key value systems treat the data as a single opaque collection, which may have different fields for every record. This offers considerable flexibility and more closely follows modern concepts like object-oriented programming. Because optional values are not represented by placeholders as in most RDBs, key value storage often uses far less memory to store the same database, which can lead to large performance gains in certain workloads. Here, keys are implemented as byte arrays and are sorted in byte lexicographical order, with the lowest order appearing first in a table, which simply means that the keys are sorted byte by byte from left to right. So after key is ordered, data subregions will be created based on the row key range. Each subregion is a basic distributed storage unit stored in different nodes. And key value pair has specific format, which contains key information such as timestamp and type, 7 parts in total. The same key can be associated with multiple values, so we can use these 7 parts to distinguish different values corresponding to the same key. Like each key value has a column qualifier. There also can be multiple values associated with the same row key and column qualifier. We know that data in HBase can be updated, so there may be multiple versions of the same data record. In this case, they are distinguished using timestamp. Here remember that HBase will return the latest version when querying without specifying the timestamp. Column family consists of one or more columns, A column is a label under the column family. Then let's see the functions and architecture of HBase. HBase consists of the following parts. HMaster involves the active HMaster and standby HMaster in HA mode. Active HMaster manages region servers in HBase, including the create, delete, modify, and query of a table, balances the load of region servers, adjusts the distribution of regions, splits regions and distributes regions after they are split, and migrates regions after a region server failed. And standby HMaster takes over services when the active one fails. The original active HMaster serves as the standby HMaster when the fault is rectified. Region server provides read and write services of table data as a data processing and computing unit in HBase. Region server is usually deployed together with the data node of the HDFS cluster to perform data storage. Client communicates with HMaster and region server by HBase RPC mechanism. The client communicates with HMaster for management and communicates with region server for data operation. And Zookeeper provides distributed coordination services for processes in HBase cluster. Each region server is registered with Zookeeper so that the active HMaster can obtain the health status of each region server. HDFS provides highly reliable file storage services for HBase. Almost all HBase data is stored in HDFS. Inside of a region server, there are the following 5 components: store, memstore, store file, hfile, and hlog. A region consists of one or multiple stores. Each store corresponds to a column family, and the store contains one memstore. Data inserted to a region by client is cached to the memstore. When the memstore capacity reaches the upper limit, region server flash data to the memstore to HDFS. As more data is inserted, multiple store files are generated in a store. When the number of store files reaches the upper limit, region server merges multiple store files into a big store file. Hfile defines the storage format of store files in a file system. Hfile is actually the underlying implementation of store file in HBase, and hlog prevents data loss when a region server fails. Multiple regions in a region server share the same hlog. HMaster manages region server in HBase, include create, delete, modify, and query of a table, balances the load of region server, adjusts the distribution of region, splits region and distributes region after it's split, and migrates region after region server expires. HMaster is in active standby mode. A cluster can have 2 HMaster processes. When the cluster starts, the processes compete for being the active HMaster. There is only one active HMaster, and the standby HMaster process is in the waiting status and does not involve in cluster transactions when the cluster is running. Region server provides read-write services of table data as a data processing and computing unit in HBase. The region server is usually deployed with the data node of HDFS cluster to store data. All reading and writing requests of user data are handled based on interaction among regions on region servers, and regions can be migrated between region servers. In HBase, A data table is divided into subtables based on the range of key value to implement distributed storage. A subtable is called a region, which is the most basic distributed storage unit in HBase. Each region is associated with a key value range, which is described using a start key and an end key. For example like this, region 1 has the start key row 001 and end key row 010. Each region only needs to record a start key because its end key serves as the start key of the next region. There are two types of regions, meta region and user region. Meta region records the routing information of every user region. The address of meta region is stored in the root table in Zookeeper, and the address of user region is stored in the meta table. Column family is a physical storage unit of a region. A table consists of one or multiple column families horizontally. A column family can consist of multiple random columns. A column is a label under the column family, which can be added as required when data is written. The column family supports dynamic expansion, so the number and type of columns do not need to be predefined. Columns of a table in HBase are sparsely distributed. The number and type of columns in different rows can be different. And Zookeeper provides distributed coordination services for processes in HBase cluster. Each region server is registered with Zookeeper so that active HMaster can obtain the health status of each region server. The metadata table is a special HBase table, which is used by the client to locate a region. Metadata table includes HBase meta that records region information of user tables, such as region location and start and end row keys. Besides, the metadata table is splitted into multiple regions, and the metadata information of region is stored in Zookeeper. Next, let's take a look at key processes of HBase. HBase can be compared to a library. You can think region server as a floor in the library, and region is the books of a certain type. So books of the same type are stored in the same region. For example, you can think the first floor as a region server. So inside of it, there are multiple regions. Each one includes a certain type of books. Like books about general biology are stored in region 1, and books about environmental biology are stored in region 2. So when users write data into HBase, first the client initiates a request. This process is like a book supplier sends books to a library. But which floor the books should be sent to, that is to say, which region server and region should data be sent to. In order to determine that, the HBase client connects to Zookeeper to obtain information about the region server where the HBase metatable is located. The HBase metatable records information about each user region, including the range of row key and the region server where the region resides. Based on the metatable, we can locate the region server of the region to which data is to be written. After obtaining all this information, data needs to be grouped. Data group includes two steps. First, get the information of region and the region server of tables based on the metatable. That is, find the location of each region in region server, and then transfer data to specific region according to row key. Data on each region server is sent at the same time. And then the HBase client connects to region server where the region of the user table is located and issues a data operation command to the region server. The region server executes the command to write data into region. To improve data processing efficiency, the HBase client caches region information of the HBase metatable and user table in memory. When an application initiates a data operation, the HBase client queries the region information from the memory first. If no match is found in memory, the HBase client performs the preceding operations to obtain region information of the HBase metatable and the user table. In either of the following scenarios, a flash operation of memstore will be triggered. Flash is a process to persist data from memory to disk. Once flashing the memstore of the whole region flashes. That's why the number of column families should not be too many. As time passes by, the number of each file increases because service data flows to the HBase cluster. More files need to be opened for the same query, so the query latency increases. So in order to solve this problem, HBase will automatically pick some smaller H files and rewrite them into fewer big ones. This process is called compaction, which can reduce the number of H files in a column family in a region and increase reading performance. There are two kinds of compaction, major and minor. Minor compaction reduces the number of storage files by rewriting some smaller files into fewer but larger ones. And major compaction merges and rewrites all the H files in a region to one H file per column family, and in the process drops deleted or expired cells. This improves read performance. However, since major compaction rewrites all the files, lots of disk I/O and network traffic might occur during the process. This is called write amplification. Major compactions can be scheduled to run automatically. Due to write amplification, major compactions are usually scheduled for weekends or evenings. A major compaction also makes any data files that were remote due to server failure or load balancing local to the region. This figure shows more directly about the difference between minor compaction and major compaction. Minor compaction involves partial H files, while the major compaction involves all the H files. And notice that if the data size of the region exceeds the predefined threshold, a region would split into two subregions. During this process, the reading and writing services would be suspended for a short time. The reading process of HBase is kind of similar to the writing process. A client first initiates a reading request, which is like query of books in the library using a client. In this case, if the book code is specified, which is like a row key in HBase, this is a GET request, which is an accurate search. If a code range is specified, this is a SCAN request, which is a query by range. Then, to locate the region based on the metatable, After locating the corresponding region server and region of row keys, open a scanner to search for data. Because a region contains mem stores and edge files that include data, there are two types of scanner to read data in mem stores and edge files respectively. The scanner corresponding to edge file is store file scanner, and the scanner corresponding to mem store is mem store scanner. Users can get some filter conditions to return the data that matches the specified conditions. There are some typical filter types like row filter, single column value filter, key only filter, and filter list. And Bloom filter is used to quickly check whether a piece of user data exists in a large dataset. Notice that if Bloom filter returns the result that data does not exist, then this result is absolutely accurate. If it returns exist, there may be misjudgment. And data relative with Bloom filter in HBase is actually stored in H files. At last, let's take a look at some enhanced features of HBase in Fusion Insight HD. While HBase is a distributed storage database of the key value type, data of a table is sorted in the alphabetic order based on row keys. If you query data based on specific row key, or scan data in the scale of a specified row key, HBase can quickly locate the data that needs to be read, enhancing the efficiency. However, in most actual scenarios, you need to query the data of which the column value is a certain one. HBase provides the filter feature to query data with a specific column value. All data is scanned in the order of row key, and then data is matched with a specific column value until the required data is found. The filter feature scans some unnecessary data to obtain the required data. Based on the preceding description, the filter feature cannot meet the requirements of the frequent query with high performance standards. To solve this problem, the HBase secondary index is generated. It enables HBase to query data based on specific column values. Take a look at this table. When the secondary index is not used, the mobile field needs to be matched in the entire table by row to search for specified mobile numbers such as 6854912, which results in long time delay. But when the secondary index is used, the index table is searched first to identify the location of the mobile number, which narrows down the search scope and reduces time delay. HBase file stream, which is HFS, is an independent HBase file storage module. It's used in Fusion Insight HD upper layer applications by encapsulating HBase and HDFS interfaces to provide these upper layer applications with functions such as file storage, read, and delete. In the Hadoop ecosystem, the HDFS and HBase face tough problems in massive file storage in some scenarios, like if massive small files are stored in HDFS, Nemnode will have great pressure, or some large files cannot be directly stored in HBase due to HBase interfaces and internal mechanism. The HFS is developed for the mixed storage of massive small files and some large files in the Hadoop. Simply speaking, massive small files and some large files need to be stored in HBase tables. In the actual application scenario, data in various sizes needs to be stored. For example, image data and documents. Data whose size is smaller than 10 MB can be stored in HBase. HBase can yield the best read and write performance for data whose size is smaller than 100 KB. If the size of data is stored in HBase is greater than 100 KB or even reaches 10 MB, and the same number of data files are inserted, the total data amount is large, causing frequent compaction and split, high CPU consumption, high disk I/O frequency, and low performance. MOB data is stored in a file system in H file format, and save the address and size information about H files to the store of HBase as values. This greatly decreases the compaction and split frequency in HBase and improves performance. In this figure, MOB indicates the mob store that is stored on H region. Mob store stores keys and values. When reading data, mob store uses its own scanner to read key value data objects and uses address and data size information in the value to obtain target data from the file system. So this chapter mainly talks about HBase, including key value storage model, technical architecture, reading and writing process, and some enhanced features of Fusion inside HBase. Okay, that's all for HBase. Thank you.